Hello and welcome to Lesson 6.3, Properties of Planes. Today we're going to see how to actually change a plane from scalar form into vector form and vice versa. But before we go into that, just remember that the scalar form of a line dealt with a normal of a vector. So when we had a line right here, scalar equation, only in two-dimensional space, dealt with the normal. So how did it relate to our directional vector? So if this was our directional vector, this was our normal vector right here. The normal dotted with the directional vector equals 0. Well, likewise, for a plane, you also have a normal vector, which is orthogonal to the plane. Now, please remember that a plane consists of two basis vectors. So remember that any plane that we might have might actually consist of basis vectors. Let's call them u and v. Well, that means the normal has to be orthogonal to both of them. So how do you figure out a normal that's orthogonal to vectors u and v? Well, we know that to calculate the normal, you use the cross product of the vectors u and v. I'll give you something that's orthogonal. And we commonly refer to this in component form as capital A, capital B, and capital C. Therefore, we get the equation ax plus by plus cz plus d equals 0, where the values n for our normal is based on a, b, and c. And you can figure out the value d just by substituting a point in the plane. Let's call that point x0, y0, z0. Substituting it in for x, y, and z, and solving. So you don't have to actually memorize this value for d. All you have to do is be able to solve for it in your expression. So let's talk about how we can create this. So we're going to create the scalar equation of a plane that consists of these points. Last day's work, we saw how to actually take a look and change this into vector or parametric form. So again, we are going to need two directional vectors. So one of my directions, just take the subtraction of any two of these points. Doesn't matter which points you choose. And so I get one directional vector of 1, -7, and 0. If I take my second directional vector as subtraction of these two vectors, I get 2, -5, and -3. Assuming I've done my calculations correct. Okay, so notice that these two directions are not the same values. That's good. So, in order to now calculate my normal, I'm just going to take the cross product between these two. I'm going to use my little trick, so I'm going to write 1, -7, 0, 1, -7, 0 off to the side, and 2, -5, -3, and 2, -5, -3. Again, this is how I work a cross product here. So I get the value of 21 minus 0. I get 0 plus 3. And I get negative 5 plus 14. Well, what you might notice is another possible normal for here, because all these numbers are multiples of 3, I can actually divide everything by 3, and another possible normal would be 7, 1, and 3. So now to figure out my equation, so I start out with 7x plus 1y plus 3z's plus an unknown value d equals 0. I choose any one of my points above to substitute in for x, y, and z. Doesn't matter which one I choose. They should all give the same result. And I solve for d. So therefore, my equation is 7x plus y plus 3z minus 28 equals 0. And this is the scalar form of the plane. If you've done this properly, the first value is not negative, and all these values should be in the lowest terms. In other words, there should be no value you can divide everything by. Okay, so we're going to be given the line 3, 10, negative 1 plus t times 7, 1, 3, and I want to determine its relationship to this plane. So I'm going to write the equation of the plane again here so that we can compare it. So I encourage you guys to pause the video and write down what you think might be the relationship to this plane. In other words, how does the plane and the line interact with each other? So if you notice, 7, 1, and 3 right here is a direction of this line. 7, 1, and 3 is a direction of the normal of the plane. So my plane, given by this equation, 7x plus y plus 3z minus 28 equals 0, has a normal like this. And that normal is 7, 1, and 3. Remember, this plane keeps extending in all directions. Well, my line, given by the equation r, had a direction also of the same vector, exactly the same vector, 7, 1, and 3. So what you can see right now is, therefore, the line is perpendicular to the plane, and therefore will intersect at one point. A little later we'll figure out how to find out what that point would be. At this moment, all we're doing is looking at how they compare to each other. Okay, so with that being said, let's move on to part C. So now we're given the line 3, 10, negative 1 plus t times negative 1, negative 2, 3. Determine the relationship to the plane. So again, my plane's equation was 7x plus y plus 3z minus 28 equals 0. At this moment, I'd suggest you pause and try to figure out the relationship to this plane. Well, in this case, what you'll notice is the negative 1, negative 2, and 3 do not relate to the 7, 1, and 3 that you can see right away. So another possibility is take a look at how 7, 1, and 3, when dotted with -1, -2, and 3, works out. So this works out to be -7 minus 2 plus 9, which equals 0. So what that means now is our plane have this normal of 7, 1, and 3, and our line had a directional vector that was orthogonal to that one. So that directional vector turned out to be -1, -2, and 3. So this gives us two opportunities, or two possibilities that come out of this. Therefore, the line is either parallel or in the plane. The only way you can tell if it's in the plane is if this point, 3, 10, -1, also fits in the plane itself. So we just need to see if that point is sitting inside the plane. And how we can tell that is just determine whether or not 7x plus y plus 3z minus 28 equals 0 if 3, 10, and -1n is substituted for x, y, and z. So that's what we're going to check. So 7 times 3 plus 10 plus 3 times -1 minus 28. Now we do not set it equal to 0 because we're not sure what it equals yet. That's what we're looking for, what the value is. So this is 21, this is 10, this is minus 3, this is minus 28. So 21 plus 10 is 31, minus 3 is 28, minus 28 is 0. So therefore, the line is in the plane. And there we go. And thus concludes this lesson.